All right, so far we've found the field due to a point charge. We've calculated the field at any point in space due to an array of point charges, and we've done that using superposition, finding the field at some point in space due to each of the discrete number of point charges and adding them all up. And now we've even allowed the number of point charges to go to infinity, and we've found the field at any point in space by essentially first turning this continuous distribution into a collection of a finite number of small elements of charge, treated the field due to each of those small elements as a point charge, found the field at some location in space, and then used calculus techniques, essentially letting the number of little differential elements go to infinity while their size becomes infinitesimal, and in that manner adding them up to find the point in space. And we've done that for a set of several different, well, I guess I'd call it specialized point charges, one of which was the parallel plate capacitor that you've seen any number of times now. And in this particular problem, what we're doing is taking the fields from two charged disks and showing that in the same way that you found electric fields by adding up the fields from a point charge, you can also find the field by adding up the fields due to the distribution of charges. So before we start, there's one thing I really want to caution you about. This formula that you see up at the top, this formula is the formula for the electric field due to a charged disk on the axis of that disk. It does not work as you get off that axis. Now it does work if you begin to move very far away from the disk, far in terms of a large multiple of its radii. Because there, the disk just looks like a dot in space. It just looks like a point charge, and that expression will, in the limit that z, the distance gets large, look like a point charge too. But if you're not in that far field, as you get off the axis, this formula very quickly becomes very inaccurate. But that's not what we're doing right now. What we're asked to do in this problem is we're asked to find the electric field at the midpoint between the two disks, and then we're asked, having at once calculated that field, what the force would be on -1 coulomb of charge at that point. So again, what we're going to look for is the electric field at x is equal to L over 2, okay, in the first case, and then we're going to try to find the force on -1 coulomb of nanocoulomb of charge at x equals L over 2. Okay, won't take very long, because we're given the expression there for the electric field due to a disk. The disk on the right has positive charge. The field points away from the center of that disk. Field on the left has negative charge. The field on either side points towards the center of the disk. And so that point in the middle has a contribution pointing back towards the origin from the positively charged disk and pointing in the same direction due to the negatively charged disk. So we really have to just calculate the field of one and double it, and that will be the total electric field at x equals L over 2. So if I just copy back down that expression, I'm going to say E disk is equal to eta, which is the surface charge density over the permittivity of free space, all times this expression 1 all over z. Z is the distance from the axis of either disk, all of the square root of z squared plus r squared. Okay, so all we have to do is put in some numbers. The field of one of the two disks is the surface charge density. That's just the total charge all over pi r squared. And I'm going to just trace down everything else here, because at this point now I'm ready to go ahead and insert some numbers. So let's do that. The one disk then is, actually what I'm interested in now is E, which is 2 times the field of one of the disks. So I'm going to get 2 times 50 nanocoulombs, all divided by pi, all divided by r squared. So r is 5 centimeters, so that's 25 centimeters squared, and I'm going to need a conversion over here from meter squared to centimeter squared. And epsilon sub O, right, is 8.85 10 to the minus 12. Just barely jammed that in there. It has a coulomb squared on the bottom, a newton meter squared on the top. And times this factor over here. Now in this case, I can write this as 1 minus L all over 2 times the square root of L over 2 squared plus R squared. And, sorry, I needed to insert 20 centimeters here, 5 centimeters here, and 20 centimeters here. And when I do that and I do the entire calculation, I'm going to end up with E is equal to 7.6 times 10 to the 4th newtons per coulomb. And that's the proper units for an electric field, yeah. And you can see that that indeed is what we ended up with here. Here's a coulomb, here's coulomb squared, there's the coulomb on the bottom. Centimeters squared cancel centimeters squared, meters squared cancel meters squared, you end up with, as we have here, newtons per coulomb. And this points towards the origin, all right? I'm tempted to put a minus x hat, I hat unit vector on it, but I'll just say points to the left, points left, okay? And to finish this problem off then, this field that we're looking for is just minus 1 nanocoulomb times 7.6 times 10 to the 4th newtons per coulomb. And so that force is 7.6, I'm going to say minus 7.6, 10 to the minus 5 newtons. And that points to the right. The electric field was pointing to the left. The negative charge flips the force and points back to the right. All right.